Hello everyone. This is the explanation video for Lab 10, Thin Lenses. In this lab, we will be studying the thin lens formula in a variety of different ways. So to remind you, the thin lens formula is 1 over P plus 1 over Q equals 1 over F, where P is the object distance, the distance from the object that's emitting light to the lens. Q is the image distance, the distance from the lens to where the image is. And F is the focal length of the lens. So real quick, in this lab, for the object distance, we're using SO. So this will be 1 over SO. The image distance is 1 over SI, and the focal length will still be F. In the first part of this lab, we will know the object distance, and we'll know the focal length of the lens that we're using. So we'll be looking for the image distance, the distance that the lens projects the image. Since we're looking for the image distance, I want to solve for SI in that formula. I can do this by subtracting 1 over SO from both sides and then inverting both sides of this equation. Okay, so that formula should give us the image distance. First, we're going to do this theoretically. The setup that we have has the light source at 10 centimeters. It has the lens at the 25 centimeter mark. This tells us that the object distance is 15 centimeters. The focal length of the lens is 10 centimeters. That's what it means to be a 10 centimeter lens. So therefore, if I'm looking for the image distance, I can do 1 over 10 minus 1 over 15, and then invert that whole thing. And if I do that, I should get 30 centimeters for the image distance. This tells us the image will be projected 30 centimeters from the lens. Since the image distance is a positive number, the image will be a real image. It will be to the right of the lens. I gave you a table in lecture 23 that can help you keep track of that. So we know that the image will be 30 centimeters to the right of this lens. If the lens is at 25, the image will be at 55. But we still don't know two things. We don't know the orientation of the image, and we don't know the magnification of the image. This is why I just drew a straight line here. We don't know if the arrow is going to be pointing up or down, and we don't know how long the arrow is going to be. To find this out, we use the formula m is equal to h prime over h, which is equal to minus q over p, or in this case, minus si divided by so. So then the magnification will be minus 30 centimeters divided by 15 centimeters for the image distance divided by the object distance. This gives you minus 2. Okay, so then there's two things here. The minus sign tells you that it's inverted. So the arrow should be pointing down. And the 2 tells you that it's 2 times as large as the object. So let's erase these lines. We know the arrow should be pointing down, and it should be twice as large as the object. So this is our prediction for what we will find in experiment when we watch the video. Note we can also do this with ray diagrams, but it's very difficult to get it exactly correct. Okay, with a little movie magic, I drew the ray diagrams on here. Let's first note that this is a 10 centimeter focal length lens, so the focal points will be 10 centimeters to the left and right of this lens. If the lens is at 25, you'll have focal points at 15 and 35. Okay, then what I have drawn is the first easy to draw ray is the horizontal to focal point ray, and that one passes this way. So that is the first one. The second easy to draw ray is the one that goes through the focal point, and then when it hits the lens, it goes horizontal. So that's the second easy to draw ray. Also note that the lens here it's just the image of a lens. I guess when you're drawing the ray diagram, you have to actually imagine the lens to be a bit bigger than is actually shown in the picture. Okay, anyway, the third easy to draw ray is the one that goes straight through the center and doesn't refract at all. And you'll notice they all meet at basically exactly the location that we calculated. For this lab, I think the lens formula and the magnification formula will be easier to make your predictions, but it's also good practice for ray diagrams. In any case, this is our theoretical prediction. Down below this, we have a spot for the experimental result. So let's check out the video and see what the video shows. So note that I'm going to be skipping through the video, but you should watch it in full. First, we show the setup for the lab. You have the object light source. This is at the 10 centimeter mark. The setup we have here, shown here, is actually for the last part of the experiment. So we have a lens in the middle, and then we have a viewing screen on the far end. So notice on the light source, you have an arrow that's pointing upward. That will represent the arrow that we are studying in the lab packet. Okay, this little note here says, while you're watching the video, the image that we finally focus on will often look fuzzy. That's because of the way the camera was capturing the light. When we were doing the experiment, we adjusted the viewing screen so that the image was as clear as possible. Okay, and this is where we start part one of the experiment. We are using the 10 centimeter focal length lens. The lens is at the 25 centimeter mark for trial 1. Here is where I adjust the screen until the image comes into focus. So notice that the image that we found is inverted, which is what we predicted with our the lens equation and the magnification equation. And the image, so when the image came into focus, the viewing screen was placed at 54.3 centimeters. So then I'm going to go back to my lab packet. I'm going to make a note that the image position was 54.3 centimeters. Okay, so that tells us the image position. The image is going to be located roughly right here. Notice that the image position is different from the image distance. the image distance is the distance from the lens to where the image is located. So to calculate SI, I have to take that 54.3 and subtract off the position of the lens. If I do that, I get 29.3 centimeters. So then the image distance SI is 29.3 centimeters. Okay, we also noted that in the video, the image was inverted, so the arrow is pointing downward. Now it's going to be very hard for you, impossible basically, for you to determine the size of the image. So we'll just use the 2 that we predicted from before. So then we found an image at that position. So notice this is a pretty good result. We found above that the theoretical image distance was 30 centimeters, and experimentally we found that the image distance was 29.3 centimeters. So that's pretty good. We also found that the image was inverted, which is what we predicted as well. Okay, so we got our results and we are happy with our results. So we will move on to the next part of the experiment. We will be using the same lens. We are just changing the object distance. Now, instead of the lens being at the 25 centimeter mark, it will be at the 30 centimeter mark. So now in this part, you have to do all that theoretical work over again to make your prediction, and then you go to the video and see if your prediction matches up with what the experiment shows. So you do that for the lens at the 30 centimeter mark, and then you also do it with the lens at the 40 centimeter mark. And then after you complete that for all 3 lens positions, you can move on to part 2 of the experiment. In part 2, we're working with a lens that has an unknown focal length. So in part 2, f will be the unknown quantity. Basically, the way it works is we set up a lens with a known object position. We determine what the image position is experimentally, and from that we find the focal length. So the equation 1 over SO plus 1 over SI equals 1 over F will give you a focal length of 1 over SO plus 1 over SI, and then all of that to the power of -1. Okay, so that's the formula we will use for the focal length. Down here are the setups that we used. We have the object again at the 10 centimeter mark. We're going to start with the unknown focal length lens at the 32 centimeter mark. And let's go to the video to find what the image distance was, or the image location was. Okay, so I've fast forwarded to part 2 of the experiment. Trial 1 will be with the lens, the unknown lens, at the 32 centimeter mark. This is where I'm adjusting the screen to find the position where the image is the sharpest. Again, it might not look the sharpest on camera, but in real life, that's where it looked the sharpest. Okay, so when I did find that location, we find an image position of 85.1 centimeters. So then I'm going to go back to my lab packet and make a note of that. The image was located at 85.1 centimeters. Also in the video, you could see that the image was inverted. So I'll draw an upside down arrow right there. Again, it's difficult to tell the magnification of it, but luckily for this part of the experiment, we don't need it. What I do need is the image distance. That's the distance from the lens to the image position. That will be the 85.1 minus the position of the lens, 32. So that'll give me 53.1 centimeters for SI. 53.1. Okay, now I want to calculate the focal length. So I do F is equal to 1 over the object distance here being 22 centimeters. So I do 1 over 22 plus 1 over 53.1, and then I take all of that to the power of -1, which gives me 15.56 centimeters. Okay, for trial 1 of this part of the experiment, I found a focal length of 15.56 centimeters. Okay, then you repeat this whole thing for trial 2, and you have to watch the video again for trial 2. And then you do the same thing for trial 3. And at the end, you'll have 3 different focal lengths, one for each of the trials. To calculate the experimental focal length of this lens, you just calculate the average of those 3 focal lengths. So f1 plus f2 plus f3 divided by 3. Note that the lens itself did not have a focal length labeled on it. So even to me, the focal length is unknown. For this reason, I don't have a theoretical or an actual value to give you so that you can do a percent difference. But do keep in mind that I have done the experiment, so I do know what the answer should be for the experimental focal length of this unknown lens. And then finally, you move on to part 3 of the experiment, where you deal with a combination of 2 lenses. The setup is shown at the bottom. You have the object at the 10 centimeter mark. You have a converging lens, a 10 centimeter converging lens at the 30 centimeter mark, and you have a -15 centimeter diverging lens at the 40 centimeter mark. So basically in this part of the experiment, you are going to, the theoretical part will be using the thin lens equation twice to calculate the final image position. And then the experimental part will be the video part, where we determine where the location of the image is experimentally. Note that it's also possible to do this with ray diagrams, but it's not nearly as straightforward as the ones I was doing in lecture or even up above in this lab packet. So I'll just show you real quick how to do that in this figure right here. Okay, so here's what the ray diagram would look like, but it's not at all obvious how this came about, and this is not even something that you could recreate in all cases, so let me explain it real quick. Note, this is not necessary for your understanding, but in case you're curious as to how this came about, here's the explanation. Okay, so I started at the object with the first easy to draw ray that goes horizontal. When this ray passes through the first lens, it refracts toward the center of that lens because it's a converging lens, and the first easy to draw ray should go horizontal to focal point. The focal point for this 10 centimeter lens just so happens to be at the center of the diverging lens. Okay, so then the horizontal to focal length ray for the first lens looks like the one I just outlined. Okay, so now ignore the first lens and let's just look at that last ray I drew. Notice that this ray just so happens to go through the center of the diverging lens. that means that this ray just so happens to be the third easy to draw ray for the diverging lens. That means once it passes through the lens, it does not refract at all. So when this ray starts going toward the center of the diverging lens, it just keeps going in the same direction. So then the final outgoing ray will look as drawn here. Okay, that explains the first ray. For the lower ray that I have drawn, I start at the object, and I start with the second easy to draw ray for the converging lens. So it starts by heading through the focal point of the converging lens, and this again is 10 centimeters from the left of the lens. When the focal point ray gets to the lens, it will refract to be horizontal. So it will look like that. Okay, now this horizontal ray, now we're ignoring the converging lens. This horizontal ray just so happens to be the first easy to draw ray for the diverging lens. So for the diverging lens, the horizontal ray, after it refracts, will look like it's coming from the focal point on the left side of the diverging lens. So the diverging lens has a focal point at 15 centimeters. So that final ray should look like it's coming from this point. And that's how I determined that final ray. Okay, so let me erase that, and the two final rays, after they have passed through that diverging lens, they will look like this as shown, and they will meet at this point right here. Okay, so using ray diagrams, we predict that the final image will be located right here. So then, to be specific, for our ray diagram position, for our ray diagram prediction, the image position will be 70 centimeters. The image will be inverted because the arrow is upside down, and the final image is 3 times the size of the initial object. So we predict a magnification of 3. Again, this was just how to do this in this particular case for ray diagrams, but when you do it in the lab below, you'll use the lens formula twice, and it's more straightforward in my opinion. Now, to start with theoretically, I am looking for the image position. So I want to use the formula that we found above, 1 over f minus 1 over SO, all that to the power of minus 1. The focal length of this lens is 10 centimeters, so I do 1 over 10. The object distance is 20 centimeters. And that would be this 20 centimeters right here. And then I take all that to the power of minus 1, which will give me 20 centimeters. Okay, so theoretically we are predicting an image somewhere at that location, 20 centimeters from the lens. We can also calculate the magnification with the formula minus Q over P. This gives me minus 20 centimeters over 20 centimeters, which is minus 1. Okay, so the minus sign tells us that it's inverted, so the arrow will be pointing downward. And the 1 tells us that the object will have the same size as the image. The image will have the same size as the object. So then this is our theoretical prediction. To find the experimental result, we go back to the video. I have fast forwarded to part 3, where we have the positive 10 centimeter lens and the negative 15 centimeter lens. We have them set up in the proper locations. And this result is with just the first lens in place. So with only that converging lens, we find an image position of 49.9 centimeters. So I go back to my lab packet, and I'm just going to make a note of that. The image position was 49.9 centimeters. Okay, already we can see that that's very close to the 50 centimeter image position that we found theoretically. To calculate the experimental image position, I take that 49.9 centimeters and I subtract off the position of the lens, which gives me an experimental image distance of 19.9 centimeters. Okay, so our theoretical result was 20 centimeters for the image distance, and our experimental result was 19.9 centimeters. So this result's pretty good. Also, if you check the video, you'll see that the arrow in the image was inverted. And again, it's hard to tell, but the arrow would have been the same size, the image would have been the same size as the object. That was the analysis with the first lens, but it's a combination of 2 lenses, so now I have to consider only the second lens. To do that, I take this result we got for the first lens and I transfer it down to this diagram right here. So I've copied that exactly from that top diagram into this diagram. The image was at 50 centimeters and it had a height of half a centimeter in this case. The image from that first lens will be treated as the object for the second lens. So the note on the side here says that this original object is no longer the object. So this is now the object for the second lens. The object distance will be the distance from the object to the lens. In this case, it is 10 centimeters. But there's one little tricky part. Since this object is not on the same side of the lens that the light is coming from, remember the light is coming from the object, the actual object over here. Since this object that we're dealing with is not on the same side of the lens, I have to treat it as a virtual object. That means I put a minus sign in front of the number. This is something that I skipped over in lecture, and I said I didn't really want to talk about it in general. This is the only time that it will come up. In any case, we are looking for the image distance, the theoretical one. The formula for that is 1 over f minus 1 over SO, all to the power of minus 1. Then plugging in the values I have, f is minus 15 for the diverging lens, and then I do minus 1 over negative 10. And I raise all that to the power of minus 1. If you plug that into your calculator, you should get an image distance of 30 centimeters. So that means theoretically, you are predicting an image to be somewhere at this location. We can also find the magnification with the formula Q over P. And I am taking the absolute value here, so I don't have to deal with the minus sign for the virtual object. But doing that, I will get 30 centimeters divided by 10 centimeters. This gives me a magnification of 3. Okay, so that means the object will project an image 3 times the size, and it will be at this location. So then our final theoretical prediction, using the lens equation twice, will be at this location and that size. You should now go back to the video of the experiment to determine where we found the final image location to be. I will leave that to you, but note that it is pretty close. And that's all there is for this lab. So once again, let me know if you have any questions, and have a good one.